All right, in our last presentation, we talked about total energy in gravitational fields. And here's a great application of total energy. It's being able to calculate the escape velocity of an object, which is the velocity that an object requires in order to escape the gravitational potential of a planet. So if I'm sitting on top of a planet, okay, I'm at a particular gravitational potential, how much energy would I have, kinetic energy would I have to be able to be launched to an infinite distance away? Okay, and this is just basically a simple application of conservation of energy. Once we have our total energy or the gravitational potential, our gravitational potential energy at that point, I can be able to calculate the kinetic energy that I would need in order to raise myself out of that potential well to a point that's infinite distance away where your gravitational potential energy would be zero. Okay, this is actually a lot easier than one would think. We're going to take a look at how to calculate that throughout this presentation. Okay, so first I'm going to take a look at some graphs. If I launch a rocket with different velocities, you'll see that only one rocket, graph E, is able to escape gravity. That has a particular velocity that it needs to be able to escape it. All the other rockets either land short or end up in orbit. Okay, and if I would take a look at the total energy of that rocket for every single launch, all right, for graph A, my total energy is going to be much less than zero. Okay, so the kinetic energy is not able to surpass the gravitational potential energy, and then my total energy is going to be less than zero. So that means that my kinetic energy is going to be used up, and I'm going to be launched up to a certain height, but not that far above the ground, and then I'm going to fall back down to the ground. Okay, in graph B, I'm going to get a little further than the rocket in graph A, but my total energy is still less than zero. Okay, now in graph C, what I'm going to do is I'm going to get up to a height that reaches orbit. Okay, so that energy allows me to get to a particular distance, and if the rocket turns sideways and I still have some velocity, I'm going to maintain an orbit, but still my total energy is going to be zero, and that's a circular orbit. If I go a little further, I'm going to make an elliptical orbit. Okay, still my total energy is zero. And then if I escape altogether, like in graph E, my total energy, the minimum total energy that I have to have, is equal to zero. And that's where we start to be able to calculate or come up with an equation to calculate our escape velocity. Okay, the escape velocity occurs when your total energy is equal to zero. Okay, and so that's what we're going to do right now. We're going to prove that your escape velocity has this formula by understanding that your total energy has to be equal to 0 joules. So if my total energy is equal to my kinetic energy plus my potential energy in a gravitational field, 0 joules, okay, that's what we said, is equal to 1/2 mv squared plus negative g, the mass of the planet, mass of the object, over r. That's the formula for gravitational potential energy. Okay, and if I just rearrange the equations, okay, negative 1/2 mv squared is equal to negative g, mass of the planet, mass of the object, over r. Okay, the mass of my object, rocket, whatever I'm launching, will cancel out, which is kind of interesting. So if I launched a soccer ball or a human or a rocket with a particular velocity, they would all need the same escape velocity to escape gravitational pull. That's an interesting realization. Okay, this negative also cancels out. Okay, and then we're left with v squared is equal to 2g, mass of the planet, over the radius, and then my escape velocity is equal to the square root of 2g, mass of the planet, over r. Okay, that's it. Okay, or your escape velocity is equal to the square root of 2 times your gravitational potential. Okay, and that's how we would derive that formula. So I can calculate what my escape velocity would be on any planet. In reality, it's related to two things. It's related to the mass of the planet and the radius from the center of the planet that I'm sitting on. That's how I can calculate the escape velocity. And if you do some calculations for Earth, the escape velocity for Earth is around 11.2 kilometers per second. So if we're launching a rocket and we want it to leave and not just orbit, we have to launch it with a minimum velocity of 11.2 kilometers per second. Okay, I'm going to be giving you guys some problem sets on Flipgrid, and I'm going to assign each student a problem so that you can be able to calculate and compare escape velocities and work with total energy. All right, that's it for the higher level gravity.